So we are going to conclude this section on separable extension with some more problems. The first problem we are going to try is this. The collection of all separable elements in an algebraic extension E of a field forms a subfield of So the problem is that there is a base field F and there is a algebraic extensions here, and there are a lot of elements. All the elements are algebraic over F, but we are not considering all the algebraic elements. We are considering only the separable elements from E. Separable elements means the irreducible polynomial of that element has the multiplicity equal to 1. It cannot have multiple occurrences. Meaning, if alpha 1 is a separable element, then irreducible polynomial of alpha I1 over F has alpha 1 as a 0 with multiplicity 1. There may be other elements which has got elements with multiplicity greater than 1, but we are not considering that. We are considering only those elements with multiplicity 1. That collection forms a subfield of E. The result what we are going to use on this one is, suppose there is a field F here and a E here, and there is another subfield in between, probably we'll say L, and let's say alpha is here. So when alpha is algebraic over F, it is also algebraic over L, because alpha algebraic over F means there exists a irreducible polynomial, let's say f of x equal to irreducible polynomial alpha comma f that belongs to f of x, meaning all the coefficients of this are in F. If the coefficients are in F, definitely that belongs to L of x. So that implies alpha is algebraic over L also. But in here, the irreducible polynomial may not be like this. That may be another g of x equal to irreducible polynomial of alpha over L. For example, let us assume that this L is equal to q of root 2, and we are considering root 2 here, and this f is equal to q, and E is equal to, let's say, Q of root 2 comma root 3 comma root 7. See, root 2 is algebraic over Q, and the irreducible polynomial is x square minus 2. So root 2 is also algebraic over L, but there the irreducible polynomial is x minus root 2, because this belongs to L of x. This does not belong to L of x, this belongs to only f of x. So if you go on the higher or the extensions of f, then this the irreducible polynomial over those extensions may differ, but there is a relation here. The more you go, then if g of x is an irreducible polynomial, then g of x divides f of x. Here x minus root 2 divides x square minus 2. So we are going to use this in here. So what we need to do is see, these are all coming from E, so definitely the collection is a subset of E. Only thing we need to prove that it's a field. So what we do is, let alpha comma beta belongs to E. Then our aim is be separable elements. These are separable elements. If they are separable elements, what we need to do is, we should show that alpha plus beta, alpha minus beta, alpha over beta when beta is not equal to 0, all are in that collection. Or all are these, if alpha and beta are separable, then alpha plus beta is separable, alpha beta is separable, alpha minus beta is separable, alpha by beta when beta is different from 0 is also separable. That is our objective. That if you prove that, then the collection of all separable elements forms a subfield. So this implies alpha and beta are algebraic over E, because E is an algebraic extension, and that implies there exist irreducible polynomials. There exist irreducible polynomials, or we'll say IRR of alpha comma f and IRR of beta comma f. Since beta is algebraic over f, and f of alpha is an extension of f, beta is algebraic over f of alpha. And that implies the irreducible polynomial of beta over f of alpha divides irreducible polynomial of beta of f. Right? Beta is actually a separable element. But since beta is a separable element over f, irreducible polynomial of beta of f has beta as a 0 with multiplicity 1. And this divides this, and this has got the only multiplicity 1. That means irreducible polynomial of beta over f of alpha has beta as zeros with multiplicity 1. And that implies beta is separable over f of alpha. And that means f of alpha or beta is separable over f of alpha, which is separable over f. And that implies f of alpha of beta is separable over f. And that implies f of alpha beta, because this is nothing but alpha beta, is separable over f. Meaning every element in f of alpha comma beta is separable over f. So in particular, alpha plus beta, alpha minus beta, and alpha or beta, beta different from 0, are separable over f. And that implies the collection of all separable elements in E forms a subfield of The next problem we are going to try is this. Every algebraic extension of a perfect field is perfect. When you say perfect field, means every finite extension of the perfect field is separable. So let f be a perfect field. And E be an algebraic extension of f. So we need to show that E is perfect. So to show that E is perfect, we'll take a finite extension of E and show that that extension is separable. So let K be a finite extension of E. To show that K is separable, we take an element of K, then show that that element is separable, separable over F. So let alpha belongs to K. This implies alpha is algebraic over E, because K is a finite extension of E. Every finite extension is an algebraic extension. And E is an algebraic extension of F, that implies alpha is algebraic over F. So now we have two polynomials here. So there exist polynomials alpha comma E and alpha comma F, irreducible polynomial of alpha over E and F respectively. And now see this, F is actually a subfield of F alpha, or I can say F alpha is a finite extension of F, and F is perfect. That implies F alpha is separable, and that implies irreducible polynomial of alpha over F has the multiplicity equal to 1. And since the irreducible polynomial of alpha comma E divides the irreducible polynomial of alpha over F, the irreducible polynomial of alpha over E has the multiplicity 1. What does that mean? That means K alpha is separable over F, and that means K is separable over E. Alpha is separable over E, K is separable over E, and that implies E is perfect. Our next problem is, let f of x belongs to f of x has a 0 alpha of multiplicity v. Then v is greater than 1 if and only if alpha is a 0 of f prime of x, where f prime of x is the first derivative of f of x. This is an important result in the sense that in some textbook, even the separability is defined in terms of first derivative. So, we'll see proof. Alpha is a 0 of f of x of multiplicity v implies f of x equal to x minus alpha to the power of v times another function in x where g of alpha is different from 0. So, if you differentiate, f prime of x is equal to v times x minus alpha to the power of v minus 1 times g of x plus x minus alpha to the power of v times g prime of x. See, if v is equal to 1, that implies f prime of alpha is different from 0 because g of alpha is different from 0. If v is greater than 1, that implies f prime of alpha is equal to 0 because x minus alpha is a factor of f prime of x, and that's what we want to prove. So that implies v is greater than 1 if and only if f prime of only if alpha is a 0 of f prime of x. Our next problem is this. Every irreducible polynomial over a field with characteristic 0 is separable. How do you prove a polynomial is separable? Is separable if and only if every 0 of f of x is of multiplicity 1. So if you want, so you have to show that if you take an irreducible polynomial, then the zeros of that irreducible polynomial have the multiplicity 1. So let f of x be an irreducible polynomial. In f of x. Then let alpha be a 0 of f of x. So f prime of x is a polynomial in f of x of degree less than the degree of f of x. Because if f of x is, the degree of f of x is n, then if you differentiate this, the resultant polynomial will be of degree n minus 1. Because f is of characteristic 0. If the characteristic is not equal to 0, this may not be true. So that means f prime of x would be an irreducible polynomial of alpha if x minus alpha is a factor of f prime of x. Because the irreducible polynomial means the polynomial of the lowest degree with x minus alpha is a factor. But here f of x is an irreducible polynomial. You already assumed that. So you cannot, if you don't have any polynomial of lesser degree than f of x, that could be an irreducible polynomial for this alpha. So that implies f of x, or that means f of x, or you can say alpha is a 0 of f of x with the multiplicity 1. If it is more than 1, then f prime of x will have x minus alpha as a factor, which means f prime of alpha is equal to 0, which means alpha is a 0 of f prime of x, which means f prime of x is the irreducible polynomial, which is not true. So that implies f of x is separable, because alpha is a 0 of this, and we showed that alpha is a 0 of this of multiplicity 1. We'll do our last problem in this section of separability or separable extensions. It is this a polynomial f of x in f of x has a 0 of multiplicity greater than 1 if and only if f of x and f prime of x has a common factor. where f prime of x is the first derivative of f of x. It's very simple. It's actually comes from the previous result. So let us assume that let alpha be a 0 of f of x with the multiplicity v. Then x minus alpha is x minus or you can say f of x is equal to x minus alpha to the power of v times g of x, where g of alpha is different from 0. So f prime of x is equal to v times x minus alpha to the power of v minus 1 times g of x plus x minus alpha to the power of v times g prime of x, where g prime of x is the first derivative of g of x. So if v is greater than 1, then x minus alpha is a common factor. Of f of x and f prime of x. Otherwise, f and f prime of x does not have a common factor. Meaning if it is equal to 1, then it doesn't have a common factor. And that's what we want to prove.